Welcome to The Explainer. Today, we're going to pull back the curtain on something you use constantly, every single day, but probably never even think about, the incredibly powerful language that lets us talk to huge amounts of data. Let's dive right in.
I mean, really, stop and think about that for a second. You tap a button on your phone and poof, in the blink of an eye, one single transaction from like 5 years ago is pulled from a sea of millions. How on earth does that happen? Is it some kind of digital wizardry?
Well, the answer isn't magic, but it's actually way more elegant. It's a very specific, very structured language that's designed for one thing: asking questions to enormous collections of data and getting answers back instantly.
And when we say enormous, the scale of data we're talking about it's almost impossible to imagine. Before we can really get the solution, you've got to first appreciate the problem, right? The absolute chaos of it all.
Every click you make, every single thing you buy, every show you watch on a streaming service, it's all a tiny piece of data. And all those little pieces are connected. Your viewing history is tied to your account, which is tied to your payment info. It's this huge, tangled web, not just a simple list.
So how in the world do you manage that mess? Well, the first and most critical step is you have to impose some order. You take all that tangled, messy data and you organize it into clean, simple, structured tables, just like these ones for employees and departments. All of a sudden, everything has a home. Okay, so our data is organized. Great, but now what? How do we actually work with it? We need a set of rules, a kind of grammar for data. And this foundational blueprint, the core theory behind everything, is called relational algebra. Now, in the database world, we don't just say table. The formal, kind of mathematical term is a relation. And all it is really is a table with columns, which we call attributes, and rows, which we call tuples. It's just a structured way to hold our data.
And you can see how this breaks down visually right here. The entire grid, that's the relation. Each single row of data, like the one for Smith, that's a tuple. And each column header, like S-name or city, that's an attribute. Getting this vocabulary down is absolutely key because everything else builds on top of it.
So, let's be super clear here. Relational algebra is the pure theory. Think of it like the mathematical proof that shows you how to get the data you want. It's not a language you or I would ever type. It's the logic running deep inside the database engine, figuring out the smartest, most efficient way to get your answer.
Okay, so if relational algebra is the blueprint, what's the actual tool we use to build with it? Well, that's where we jump from the pure theory into practice, with a language that millions of people use every single day.
And this right here perfectly nails the core idea. On the left, you've got relational algebra. That's the abstract mathematical blueprint. On the right, you've got SQL, which stands for Structured Query Language. That is the practical, real-world tool that brings the theory to life. It's the blueprint versus the hammer.
And get this, just take a look. Down on the bottom, you have the dense mathematical notation of the algebra, and up top, you have the SQL query. You can literally see how one translates into the other. SQL was designed to be a much more human-friendly way to express the exact same powerful logic.
So, how do we actually use this tool? Let's go over the basic grammar for asking our first questions.
What's really cool is that a basic SQL query reads almost like a simple English sentence. You just select the columns you want, then you say from which table to get them, and finally you filter it where a specific condition is true. And these commands map directly back to our blueprint's ideas. Choosing columns is project, and choosing rows is select.
Here's a perfect example in action. We are literally telling the database, hey, select the country ID and the country name from the countries table, but only give me the ones where the region ID is 1. It's simple, it's powerful, and it's perfectly clear. But what happens when the information you need isn't all sitting in one neat little table? This is where the real power kicks in.
So for efficiency, data is very often split up. Look here. On the left, we've got a list of departments with the department number, and on the right, we've got employees who also have a department number, but they don't have the department's name. So how do we connect an employee to their department name? This is our goal. We want one single, clean list that shows each employee's name right next to their full department name. To do that, we have to tell the database exactly how to match up the rows from those two separate tables.
And the magic word that makes this happen is called an inner join. It's a simple instruction. It just tells the database to combine rows from two tables whenever it finds a match. In our last example, that's whenever the department number in the employee table is the exact same as the department number in the department table.
So you see, these simple building blocks are so much more powerful than they first appear. They are, and this is no exaggeration, the code that runs our world. Every single time you search for a product online, or filter your photos by date, or check your bank account, you're speaking this language without even realizing it. Your apps are using these basic commands: select, from, where, and join to ask a question. They're the fundamental alphabet we use to talk to data. So it's not magic, it's a language, a structured, logical way of having a conversation with data. The entire modern world is really just one massive, ongoing conversation with databases. The only limit is the questions you can think to ask. Thanks for watching The Explainer.